Thank you very much, Francisco, for this introduction and for this kind invitation to come to Madrid. It's a pleasure for me to be here. I'm happy to be here and present this talk. And today I will talk about advanced mechanics of and modeling of software engineering materials. Since a long time we are doing with software engineering material. This is my group you see here, and we do also with anisotropic materials, elastomers, biological tissues, which I will very shortly mention as rather new topic as aerogels, which are very effective for aeronautic, for example, and we also, since recently, we also dealing with data-driven models, and I will also talk a little bit about it. So my talk is structured as following. We will discuss with you at the beginning mechanics of elastomer, in particular this very interesting effects in elastomers, mechanoluminescence and strain crystallization. Very short, because of lack of time, I will mention hydrogels and then focus on aerogels I already mentioned, and mostly on these two types of aerogels based on biopolymers on silicon. And finally, I will focus on these other new topics, symbolic regression, how it can be used for constitutive modeling of materials. Right, first topic is driven by my former PhD student, now postdoc Kim Wu, and first we would like to discuss with you this motivation for this topic, and this model we will discuss with you is physically based. That's why we will start with statistical foundation of molecular foundation of rubber elasticity. Then we will see how we can come from the micro level to the macro level, and then we will see with you some examples in rubber elasticity and Mallet's effect, very important for rubbers and mechanoluminescence. And here you see a typical stress-strain response of rubbers. And if you see here, there is a huge difference here between first loading and second loading. You see this difference, and this is exactly what we call Mallet's effect, right? This difference between loading and unloading, it is called hysteresis. It is something else. And this is very important, interesting effect in rubbers Mallet's effect, because if you look, the tangent line here, the very first loading and the second loading, they differ very strongly. In the third load, material becomes softer and softer with the next loading. And this should be taken into account in the constitutive model. Another important effect, also very difficult, you see, if I change the direction of loading of rubber, I load it and change the direction, the response becomes softer. That means that it is induced anisotropy. If you take a piece of rubber in the hand, apply a little bit load, it is already anisotropic, right, after we go into first loading. We also will speak with you about mechanoluminescence in this context. Another important effect, the problem is that you see here, if you add so-called dioxetan molecules to rubber, and under loading, these molecules break, and this breakage emits light, visible light, and you see here this piece of rubber which under loading begins to emit light, and in this way it is also very interesting effect. This way we can see how much damage is inside of rubber. Rubber parts are usually very cheap, O-rings for example, but if it breaks inside of the motor or something else, the damage can be huge and very expensive. So this is the application of this effect. There are many already in dynamics. Some of them are optoelectronic, biomedical, luminescence devices, and so on. So this is what we are going to discuss in this context. And I begin with very shortly with the molecular statistical foundation. You see here typical polymer chain consisting of n segments, each of the length L, and we work here with so-called freely joined chain model. It's like a chain which can rotate arbitrarily, and it is also called phantom-like because it can cross each other, which are unphysical, but this model works very good. And we see here also specify some direction, and this is the angle theta between this end-to-end direction of this chain and this direction. We also introduce this so-called relative end-to-end distance, which is the relation of this distance r to the length of one chain. And according to the classical theory of this chain, the distribution, the statistical value distribution of this relative end-to-end distance depend on the number of segments, and it describes a very, very complex here function, which is also discrete, right? It depends on the integer value, very difficult to use. There are some approximations of this function, for example, by Kuhn and Gruen, and it is given in terms of this inverse, so-called inverse Langevin function, but it is itself not cannot be described by close mathematical expression. It needs approximation. You see here this function also has some deviation from the exact function, right? That is why the idea is to directly approximate it, and this is what we did here. We use a so-called wave particle duality, and accordingly we propose this function which fits rather good directly, not through this inverse Langevin function, fits directly to this exact distribution. You see this agreement rather good for short number of chains. This is number of chain 8 here 6. I don't know whether you can see it here or not because the quality is not quite good. And here for longer chains 24, 32, and also you see with increasing end-to-end distance, this probability tends to 0, which is clear because if you try to extend this chain to the straight state, the probability is very, very low, very almost to 0, because the energy needed to reach the state is almost infinite, right? That is why it is described in this way. Another problem is that such chain is not alone. It is surrounded by other chain in a polymer and a rubber, and this is taken into account by the so-called tube model. There is additional probability function here, and we introduce here according to this micro stretch and micro tube contraction. Here it is exactly the relation between this reference diameter of such an imaginary tube and the final diameter. And what to do with this probability? It appears here if we calculate the entropy of the system, which appears in the Helmholtz free energy. And you see here exactly if we take this logarithm of this number of states, then we get here from the product of these two probabilities the sum of these energies, and we see this energy of entropic energy of the chain and this topological contribution. Now the next question was how to come from this micro to macro level, and here we use the so-called analytical network averaging concept, which is based mostly on this known von Mises-Fisher distribution. This is very nice because it's based on the exponential function. We see here again this angle between this direction and the preferred direction, and we can have many terms depending on the anisotropy of the material. For isotropy, we can it's enough to have only 3 terms, and this zeta I is the concentration parameter for the distribution. If that is 0, it is isotropic. It can be illustrated by sphere, and with increasing concentration part becomes more and more anisotropic. You see here this distribution for only one direction, and here more complex for 21 direction, right? So any anisotropy can be described in this way, and the nice thing is based on exponential. If integrated over all directions, you see we can express everything analytically in terms of the first here and second invariant of the right Cauchy-Green tensor. I hope you are familiar with this. And Wi is this number of chains in this direction that can be expressed directly in terms of the concentration parameter. And in the special case of isotropy, we have this classical relation where stretch is this square root of the first and then divided by 3, and this tube contraction also can be expressed in terms of the second invariant, right? Let us look at the applications to rubber elasticity, for example. There's this expression of this strain energy function in this case. We have two terms in everything. We have this share modulus, so these two are parameters. We have another parameter, the number of chains, average number of chains, and I mentioned already, and additionally, we have here this stretch amplification exponent. So we have all four material constants, and you see here we compare our model with this with Trello, classical Trello data and Kawabata data. In this Kawabata experiment, biaxial tension was applied with different relation between stretches. So in two directions, we see different. And using only these four material constants, we can nicely describe simultaneously this two experimental data very nicely, right? Another interesting application is this dynamic, based on molecular dynamic simulation, namely these parameters are physically based, and we can get them without fitting. We can get them directly from molecular dynamic simulation. And then in this case, our model fits also rather good to molecular dynamic simulation, which is not the case for other models. For example, for well-known Aruda-Boyce model, also okay. Aruda-Boyce model does not include this topological part, but this new model does, and here still we have this rather big deviation from this data. Another example is inhomogeneous example was such a plate with 5 poles and subjected to tension, and along this line, this displacements were measured, and we fitted our model to this experimental data, for example, the stretch strain curve and uniaxial tension and biaxial tension. Also, you see here constraint tension, constraint compression, and finally, you see the agreement is also for this no homogeneity very good. Also, the displacements are very good described along this line. Let me now focus on Malin effect. The problem is that the Malin effect is irreversible, which means that if you loaded the material, it was already damaged, and we made an experiment, we leave the specimens, leave 1 week, and after the 2 weeks, we measured it again, and we realized this material is still damaged. So it is irreversible. It is damaged once and almost forever. And that is why it is distinguished from the hysteresis, because hysteresis is cyclic, damage it repeats many times, and that is why what to describe these effects, we consider this network of polymer chains with this aggregates inside, and consider this decomposition of this network into parts. In the first part, we have these chains which break. For example, in the case of dioxitane, they also emit light, or simply detach from these aggregates once and forever. And in the second network, we consider hysteresis. These chains can attach again after unloading. And we see here once more these effects are illustrated. Here we see again the dioxitane molecules which emits light when broken. And here you see if the distance between the two aggregates becomes longer than the contour length of this molecule, there is a gap, and this to take into account, we consider distribution of the chain lengths. You see here distribution of this length, and with increasing distance, you see here this boundary between broken and unbroken chain moves. The number of broken chain increases, number of active chains decreases, and in order to calculate this number, we integrate over the gray area, and calculate, you see once more this gap, and calculate this number of active chains available. And on this base, this model is formulated. And here you see results of this model. We compare this model with experimental data on polychloropropyl rubber with 50% of carbon black. You see rather good agreement also for hysteresis here on this below slides. In this example, it is a comparison with PDMS elastomere, also rather good agreement. And you see here in the last picture, also the number of broken chains is good predicted due to this dioxetan molecules. And last example here, this mechanoluminescence I already mentioned. In order to model it, we consider such a void inside of rubber with this dioxetan molecule C once more. And we assume from the mathematical simplicity that this void has a spherical form and surrounded by these chains, and it increases with the loading, and when it reaches this critical diameter, this molecular breaks and emits like this assumption. And then what we do, we calculate, similar to the well-known Griffiths theory, we calculate the energy of this void simply as a difference between surface energy and bulk energy of this rubber inside, which is now released when this void appears, right? And then we maximize this energy, and then in this way we get this critical diameter and energy barrier, and then this is this energy, and inserting this energy into this Boltzmann factor, we can calculate then this fraction of available chains. And again, we consider this energy barrier as a statistical value using this Boltzmann distribution. These are main details of this model. Due to the lack of time, I have no opportunity to go into details, but it is written in all our papers. Here you see comparison to experimental data with double network elastomer unfilled. You see rather good agreement. Also with the light intensity, rather good agreement with experimental data. Here it is another elastomer. These are results from the group of Professor C. Besman from Netherlands. They do this experiment with dioxetan and share these results with us. And you see here rather good agreement with this experimental data, this light intensity again. And interestingly, also the number of dioxetan molecules is very good predicted in our model. The only different deviation we have here still with this number or energy of activation energies. Right. Let me summarize this part of my talk. We have presented here a physically based model which is able, in one framework, is able to consider many different effects in rubber. Anisotropic valence effect, permanence, hysteresis, mechanoluminescence. And the model is thermodynamically consistent, and there is no need for numerical integration in order to take into account this anisotropy because of this analytical integration. We have very few number of material parameters. For example, in the case of elastic behavior is only 4, and we have a good agreement with the statement. Another topic also done by, considered by Kim Wu, also in cooperation with Professor Lecam from Institute of Physics, University of Rennes in France. He did very nice experiments for us for calorimetry, and here by means of this calorimetry, you will see we will be able to describe strain-induced crystallization. It is very interesting to get where small crystals appear in rubber only due to stretching. There is so-called cold crystallization when crystals appear when you decrease temperature. And here we consider the strain-induced crystallization very important effect for industrial application. I will talk about that a little bit. I will talk about thermodynamic framework, again about this macro transition, how these crystals appear. We will speak about kinetics of this crystallization and a little bit about numerical results. Why it's so important, this crystallization? Because if you look at the, again, stretch diagram of crystallizing rubber, we see that at the beginning we have small softening, but then very strong stiffening. This is also important. And another important thing is that these crystals nice property. They can retard or even stop propagation of cracks in rubber. And this is very important for heavy load application, for example, for tires, truck tires, and so on. However, this crystallization appears at very high. You see here this halos, X-rays, diffraction halos. By the way, it is very expensive experiment, and the very less in Germany only 2 devices where you can make this measurements. And this is ideal, this study to use this thermography in order to detect crystallization. And we see here that this crystallization begins at very high stretches, around about 4. And this high stretches appears very seldom in rubber. But around the crack tip, we have concentration of strains, and very high strains can appear here. Exactly here, this crystal can appear and retard or even stop, as I mentioned, the propagation of cracks. This is exactly what I mentioned with this thermography. In this way, we can measure this so-called heat source. And if we look, we see that, for example, at rather small cycling stretches, this diagram is rather symmetric. Amount of heat produced is equal to the amount of heat consumed by the melting of this crystal. And at higher stretches, we have here an asymmetry. And this is due to the fact that this crystallization is phase transition, and for this reason exothermic. And due to the fact that we have here no dissipation, we believe that hysteresis of large stretches at rubbers is not due to dissipation, but mostly due to strain-induced crystallization. And that is why it cannot be described by the classical model like viscoelasticity, damage of plasticity. Also, there are many models here which try to describe crystallization by means of this dissipative model like plasticity or viscoelasticity, right? We also try to do, we did it also, we described with crystallization in our recent paper, but the no colorimetric effects were discussed or non-diabatic condition was not considered. Now, let us discuss the kinetics of this crystallization. First of all, if we apply some tension to rubber, these polymer chains under tension, they come very, very close together. And when they come close together, some crystals appear here because they are very, very small diameter. And under unloading, this crystal begin to melt, but around this crystal, other crystals appear because these polymer chains begin to form such zigzag structures here, and another crystal, and another second type of crystallization, and the third type of crystallization here we see is so-called non-equilibrium crystallization. It doesn't depend on stretch. Simply, if there are some crystals already around this crystal, new crystals appear or disappear, and this is what we are going to discuss in this model, and then we will consider, as of the motion, these two types of the crystallization. And this idea of this study to integrate this thermography to take into account in the computational modeling. Again, we will use statistical mechanics and irreversible thermodynamics. We consider also dynamic of strain-induced crystallization, and also what is interesting, we will discuss or try to consider not only uniaxial tension but also multi-axial deformation here and how this strain-induced crystallization develops in this case. We begin with the thermodynamic basis. Again, we see here this Helmholtz free energy consisting of two parts. This is the internal energy, this is the entropic part, this is entropy, and this entropy depends not only on the deformation gradient, but also some internal variables. And here we see this second, third type of crystallization. They are not measurable, and stretches, maximal stretches, here in different direction, which describes this damage or viscoelasticity, and the stress of such a material as usual can be obtained as a derivative of the strain energy function with respect to the deformation gradient. And for crystallization, this thermic part is very, very important. You see here it appears here in this internal energy, but also appears in the first law of thermodynamics. And nice thing is that here, this part can be measured. That means that we can obtain this term, and in this term, this part can be calculated, and finally we can separate this amount of energy, which is, or power, which is proportional to the total crystallization. And this is the idea. If we measure temperature and heat source on the surface of the specimen, we can finally get, through this calculation, we can finally get the evolution of this crystallinity. And this is the idea. The only what we can do, we have to do again, we have to consider this how this crystallization changes this our analytic averaging concept. And the idea is to use this again, this X-rays diffraction pattern and try to mimic with our function here this distribution, and this can be done also by means of this concentration parameter I mentioned already. The idea also very similar to the Griffith theory again here. If you consider the crystallization, you see again this first type of the crystallization. These crystals appear here when these molecules come closer to each other. We assume again for mathematical simplicity cylindrical form with diameter phi and length L, and again use these two terms here, this energy, surface energy minus this bulk energy of the rubber released here in this volume, and using maximization we can get this critical values of the diameter and length, and based on this we can get exactly this what I mentioned, this concentration parameter and the number of oriented chains due to this crystallization. This is the second crystallinity you see here, and it depends on the cyclic load, it depends on the maximal stretch of the cycle, the actual stretch, if they are equal to zero. And this is the number of this crystal, it's here nucleus, which help other crystals here to appear, and they finally get this second crystallinity. And the third, this non-equilibrium crystallinity, as I mentioned, it doesn't depend on stretch. It's simply, we assume it depends on the characteristic times of crystallization and melting. If you simply keep them as a rubber unstretched or under constant stretch, some crystals, they slowly begin to melt, and we assume this crystallization to the Z is minus, and in this way we describe the evolution of this crystallity. Let us look at some results. You see here on the right hand side this experimental device in France, in Rennes, of Professor Lecam for the uniaxial tension and for the later units with biaxial tension. First, what we do, we fit our model to experimental cyclic tests with the, under uniaxial tension and uniaxial tension with this relaxation times. This is very important in order to describe these parameters of this tertiary crystallization, and you see here we get a very good agreement with experimental here. Here is this agreement is obtained automatically, for example, for this cyclic test with stepwise increasing amplitude, and also here with preconditioning. The only problem you see here in the description of this heat source, we have rather good agreement at a middle, let's say, values of stretches, and very high stretches our model overestimates the heat source, but we believe that is due to the fact that we don't consider this internal energy of the polymer segment, but temperature evolution here, for example, rather good described, and here also crystallization degree, here we have good agreement with this results. And finally, this results for biaxial tension. We see here the sample for biaxial tension simultaneously stretch in both directions, and also the results are rather good. Here, for example, for the crystallization degree. Interesting message here for biaxial tension. We observe that this crystallization appears in the biaxial tension earlier and at lower stretches in comparison to the uniaxial tension. Right. Short summary of these results. We presented here non-adiabatic thermodynamic framework of strain-induced crystallization. The model was coupled with the infrared thermography in order to measure the heat source. We obtained very good agreement with experiment, rather good agreement with experimental data, and we observed that under multi-action logic, for example, by action loading, the crystallization appears earlier and with a high intensity. And we believe that this is the first step towards the description of strain-induced crystallization based on a cheaper, let's say, and more accessible way in comparison to this X-ray diffraction, what I mentioned at the beginning. Right. Very, very shortly about hydrogels. Also, this topic is also driven by Kim Wu. Almost the same model we use here with hydrogels. Many years was the problem is that this hydrogel created, if you take it in the head, it's like a yogurt or maybe like a pudding. So it destroys very fast. And the problem was the polymer chains are broken. And this was the idea from the Professor Gon from Japan. They added second network into the first network, which stabilized it. And then this so-called double network hydrogels appear with very nice mechanical properties. Hydrogel, why they call hydrogel? Because they consist of much water. And the advantage is that they have a very good biocompatibility, environmentally friendly, and anti-biofouling behavior, and many other important also biodegradability, many important applications also in tissue engineering, soft microbiotic, drug delivery, they use also for drug delivery, regenerative medicine, the skin, artificial skin also made of hydrogen, many applications. Very short message how we deal with the modeling of iron. Skip some slide. The problem was that the so-called cross damage effect in these hydrogels. We have two in the, for example, double network hydrogels we studied. We have two networks, and the problem was that if you apply some tension, the damage appears not only in this direction you apply them. This shown here. You apply the stretching, and also this damage appears in the cross direction. That is why you call it cross damage direction. And this is what we try to take into account. You see here this parts of this network, first network, also are destroyed under tension, and also using the same idea, integrating over this gray area of the number of the active chains, we can obtain this number of active chains in this direction, and then take it into account in this analytical energy concept. You see here this comparison to experimental data, rather good agreement under uniaxial tension, equibiaxial tension, pure shear biaxial tension. Also here other results for double network hydrogels. Here for the stored energy, dissipated density, and so permanent set. Also the agreement is rather good. Right. Some results of the study. So we here proposed micromechanically based model for covalent, so-called covalent cross-link double network hydrogels, and the challenge was to take into account this cross damage effect, as already mentioned, and we obtained here also good agreement to explain. Next topic I would like to discuss with you are aerogels, I already mentioned, and here we collaborate with the German Aerospace Center in Cologne. As I mentioned, these materials are very light, and for this reason, very attractive for aeronautic application. And we work here together with my former PhD student, now Dr. Amir Rik, and he has a small department in Cologne dealing with aerogels. He says that the largest department in Germany dealing with aerogels only. Right, this is my main topic. And first, I would like to discuss with you the interesting properties. of aerogels and how they can be synthesized. And then we focus on two different types of aerogel, biopolymer and silica, and we use different methods in order to model these aerogels, and this is what we are going to discuss. What are the aerogels? So strictly speaking, our classical definition, it's aerogel is a gel comprised of a microporous solid in which the dispersed phase is a gas. Mostly it is air. We see some examples here, pictures, and these aerogels can be based on different materials, silica, metals, or organic, which are also very nice biopolymers we will discuss with you. And they are characterized by very lightweight. 99.98% of air, right? So it's mostly air in this material, right? But still, there are these properties we will discuss. And still, we have high strength and very high thermal and acoustic isolation. This is very, very important. Here's examples. Nothing happens if you apply some fire. And also here, very, very light, right? How this aerogels can be synthesized? The idea is that we have a salt with some particles or fibers also, and then such a dilation under higher temperatures, such dilation process takes place. These particles begin to form such a structure, but still we have a lot of fluid, and then so-called supercritical drying is applied. So it's not, if you apply usual drying, the structure can be deformed, destroyed. That is why some special kind of drying is applied under a special combination of pressures and temperatures, and those called supercritical drying. And then we have such a structure with air, open cells with air inside, with 99.98% of air, right? This first topic, what we are dealing with are biopolymer aerogels, and this is studied by my PhD student, Rajesh Chandrasekaran. And the idea was, I will discuss with you, to try to mimic the structure of this biopolymer aerogel by so-called Voronoi tessellation, and the another version of this Legar Voronoi tessellation I will discuss it. Right, let us speak a little bit about this biopolymer aerogels. They are based on so-called polysaccharides, for example, starch, cellulose, or chitin, and they are extremely light. 120, if you look at this number, 120 grams per cubic meter. Just imagine, cubic meter, and the weight is 120 grams. So you can take it with a small finger and keep, right? Such a huge cube. They have a very low thermal conductivity, and the problem is for the model we'll discuss with you very heterogeneous pore size distribution. We have different pores here, large pores, small pores. Also here we see the examples of the aerogels made of starch, cellulose, and kappa carrageen. And right, if we speak about mechanical behavior of these aerogels, of course, it depends on the microstructure. And this idea to describe this microstructure in this way, we will be able to tailor its mechanical properties based on these different parameters. Which parameters we can vary here? Of course, solid fraction, Young models of fibers or particles, and this so-called pore size distribution. You see here this distribution obtained experimentally. This is the number of pores, and this is the pore width, right? Pore width here also the complex function. And the challenges are here is, as I mentioned, to take into account this highly irregular shapes of the cells and extremely small pore size, and we are going to develop such a modeling technique, as I mentioned. It is based on this Voronoi tessellation. What is this Voronoi tessellation and how it works? You see here this illustration here, animation, and some seed points are distributed in geometrically with randomly distributed, and then around the seeds, this so-called Voronoi cells are placed such that these points are equidistantly distributed around, right? And if you compare, for example, this scanning electronic microscope pictures with this tessellation, so qualitatively we can see there is a good agreement, and this is already a good piece of news. However, the idea is to make it a little bit more versatile, and the idea was to apply some weights for these cells, right? And this can be done by means of this so-called Ligabron tessellation. In this case, we have more control over the cell size, and the problem was only how to choose this weight, how large should be cells. And the idea was to apply such a sphere packing. You see here the spheres. We try to feed these spheres inside of the cube, for example, and the diameters of the sphere, they serve as the weights or volumes of the weights of this sphere Ligabron tessellation. You see here then the difference between them. We can here describe this microstructure much better. Right, and this shows then for finite element simulations, it is based on this LVE with periodic boundary condition. You see here such an LVE for 2D, but it's also done for 3D, and you see here how it is then happens. Then we apply hugely beam elements for these connections. Beam contact, and also friction between these beams is also taken into account, and everything is then calculated and is doing implicit solver. The whole procedure here, the results you can see here. For example, for elastic model, you see here good agreement for stress-strain curves for different amounts of particles here, right? And also good agreement for the so-called Fowler law. This is a typical 5 minutes.
10 minutes. Yeah, because we have
yeah. Powell law, which describes the dependence of the Young models on the density here. Also, inelastic models also rather good. Here we assume here this bilinear, the strain response, and all these important effects in aerogels are described. Elastic region plateau here and densification. Here you see here this so-called densification. Here's how it is works in this finite element simulation. The whole structure is compressed. You see to 70%, and as we mentioned, we have here beams with the contact with each other. Right, I skipped some slides. Right, this is the conclusion to this topic. You see here the spheres inside of this Voronoi cells. We try to describe this microstructure by sphere packing and Ligabron tessellations. We obtain good agreement with experimental data. We obtain good agreement also for strain response, namely this plateau regime and densification are rather good described under compression. Permanent sediment histories are also described, and also we obtain the failure, can describe the failure of the fiber network under tension. And nice thing is that we, in this case, this agreement obtained without any fitting. These parameters are obtained directly from the spore size distribution. And this procedure, we believe that it can be applied also to other open cell material, not only to hydrogels. Another topic very fast, because we have less time, is studied by another student, PhD student of Mirasul Abdusalamov, and we deal here with the other kind of aerogels, the silica aerogels, and we use another procedure. It's called diffusion limited cluster aggregation. Only some words about that. Here you see, I go very fast on the slides. There's silica aerogels. And the idea is that to use this, as I mentioned, this diffusion limit cluster aggregation. The idea is that we put also some seeds and some walkers, and these walkers then they randomly walk around the seeds, and when they come closer, they connect to them and begin to form these aggregates, right? And there's the idea of this model. We see here what are the results of this model. We also apply here finite elements with LVEs and periodic boundary conditions, and also here we have rather good agreement. For example, again for this power law expression. Right. And last topic, in last 5 minutes, I would like to discuss with you this so-called data-driven modeling based on symbolic regression. I will shortly discuss with you the symbolic regression, and this topic is also studied by Rasul. The idea is that when we construct such a model, constitutive model, for example, experts, right? So we create some functions, we create some terms, and in this way we try to get good agreement with the experiment, right? So we do it ourselves. If we can do that, why it cannot be done by a computer? This is the idea. And the idea was to use the so-called symbolic regression. I will shortly give you an idea about the. First of all, the motivation came from usual data-driven modeling. And if you apply neural networks, for example, you get finally a very complex structure. You get a good agreement with experimental data, but the function you get is not interpretable. It is very difficult to implement it into the finite element code, and it can be very, very complex. And the advantage of this symbolic regression is that we can construct interpretable function, and we can search for a mathematical model in form of algebraic expression. For example, we use a package of Python, and you see here, for example, this is Mooney-Rivlin was very simple Mooney-Rivlin model with 2 terms, and we can formalize it. We can say it consists of some mathematical operation, product plus product minus some terms, right? And this task can be given to a computer, and such a generic evolution algorithm can be applied here. You see here how it happens. We have a task to find such a function, right? And with using some simple operations, power law, multiplication. So the computer starts and improves this behavior. You see this criterion is the fitness, not only fitness, but also simplicity. Optimization criteria is simplicity of the expression and also the precision, right? We begin with some random population of basic allowed algebraic operations like product, square root, whatever, cosine, sine, and then this selection algorithm I apply rather develop crossover. I will not go into details, hoist mutation, point mutation, subtree mutation, and the end we have good agreement here. The problem is also we have to compare with experimental data, not the function itself, but its derivative. That is why we have to calculate automatically this derivative, and after that we get stress, and the stress can be compared with experimental data, and this way we can get so-called fitness of this model. Some examples here see for this generalized Mooney-Rivlin model with 5 terms. Here you see the fitness improves decreases very, very fast, and we have good agreement here with experiment with this original model, not experimental data, it's original model here, and for the 3 sets of this material constant. Another idea was to model not only hyperelastic material, but also include some other parameters, for example, here temperature. And we got from internet, for example, set of experimental data of a polymer for different temperatures between -40 and 120 degrees. And some of the data we used for fitting, and another data was for curves were used for testing. And you got very strange, but still interpretable function. And you see here This is a training set. We have a rather good agreement here also. And this is a test that this data was not seen by the model. It tries to accept maybe for some here parts. It still showed very good agreement with experimental. So let me summarize as part of the talk. We have shown that we can nicely create this hyperelastic material model by the symbolic regression. The important thing is that continuing framework is here preserved, and we can easily integrate it into the commercial finite element packages. We finally get this physically interpretable, as I mentioned, data-driven model, and we are going to extend it to other parameters, not only hyperelastic one. So thank you very much for your attention.
Just a couple of questions. Is my sure has a question?
I'll start. Thank you very much for your talk. Sorry, stuff. So I started my PhD with the elasticity and with machine learning models. So I kind of relate the first part and the last part of the talk. But currently I'm working on topology optimization applied to metamaterials. So at some point of the talk, when you were discussing about the aerogel, you presented the power law for the stiffness for the Jones modulus.
Yeah.
So does this mean that the penalization procedures for topology optimization are correct to use, like the power law? Because you proved that like experimentally,
Well, yeah, you see, power law is the let's say very typical for physicians, right? Because they have nothing more. And of course, power law is only the first step, because Young modulus is only one value we have at the very beginning, very small strength, right? It's only first try to get some first characteristic of a maximum. Of course, it's not enough, and you have seen we tried then further to model this stress strain characteristics. Not only, but it's a first, let's say, step of the Young modulus and power. Right? They don't like it also, but in literature it's very distributed. If you look the literature about physics or the variables, there are very many approximations based on its first step. Its first possibility to connect Young modulus with the density. Right? Density is very easily measurable. You calculate volume, weight, and then calculate density, and by means of this, Paolo can immediately evaluate Young modulus. Right? That is why it's very first value which gives you as an engineer, let's say, first important characteristic of material.
Thanks.
No question? Alberto? Yeah?
Thank you. I have a question. I realized that Salva and professor are working on hydrogel elastomer hybrid. What would happen and how can we model Salva's direction?
Good question. Maybe I suppose that this hybrids of hydrogels and elastomers also a way to improve the properties of hydrogels, or maybe vice versa of elastomers, right? Make elastomers more biocompatible. First idea would be to use this decomposition of network, because I suppose there are different networks. You can consider that inside you have a usual network of polymer molecules which are cross-linked like in an elastomer, but there is another network of hydrogels and there is a water inside. So it is the question is rather general to answer it immediately, right? So maybe water can also play a role here inside of elastomers. Right?
Thank you.
Yeah.
More questions? No? I have one last question. Yeah, with the analytical integration, basically, I didn't get the idea that the thing is basically you decompose in different functions that you integrate analytically. Because it's the summation, basically that, no?
In this case, can be directly integrated because of this cosine.
That's 21. Right?
log rate. Or, yeah. No, this here we don't need it because this function is based on exponential, and it is possible to integrate it analytically. And here we have this first thing. If it is zero, that's a classical case. Here you have isotropy. The only difference is here with this concentration parameter. Then we have here additional terms where you see this lambda I is a stretch in this particular direction, and this function becomes so extended in one direction as you have seen here. Here, right? You see, for example, right? But the function is rather easy to integrate, and that is why for me distribution, that is why we're choosing this function in order to get another.
The summation is basically that you are decomposing the function.
Summation is only to use different terms. If you have a complex case of anisotropy, you can take many terms. It depends. You can take one term, you can take many terms, right? For isotropic materials, usually it is enough to have three. But if when we deal with rubber, this inducing isotropy appears, many terms are needed. That's why we also said, okay, difficult case 21 directions, right? But of course, it is numerically expensive if you apply this integration set.
I have another question.
Yeah.
I think that is because they have relatively, no? Yeah, they have plus. Yeah. So okay, so let's take a look. You want to does he have class like he's a business student, so he can ask you the question. I mean, just ask the question because the other ones have to leave. So you can ask the question.
I have a question. For probability distribution for polymers, we use different theory, for example, Gaussian. And for different domain of the stress domain, or we have a different domain, or can we use a combination of probability? Because in some part, you know that the chain and entropy is high and some is maximum and some.
Why not? I would not say maybe no. Why not? If it is show good agreement, I would not say no immediately.
So it's mathematically and physically, is it possible to use different?
Why not? All this finally, okay. Gaussian distribution results from this chain statistic, from this random walk theory, right? Directly. So it is physically motivated, right? But all other, okay, not quite, right? So not Gaussian also can be motivated from, but if you say that this physical motivation not so quite important, can take a combination. Also, as I mentioned, it will be difficult maybe to reason it from the physical point of view.
Yeah, the subdistribution is the formula to put it.
Yeah,
because it's a combination central.
And what about Bingham? Can we use Bingham for general hyperelasticity?
I think so. But, difficult to say. In which problem you for elasticity? What is it? It is a rubber, a general elastomer. What is?
For example, I want to use it and check it with ruler or COMETAS and see what would happen. Oh, I know Bingham has been utilized. I just saw a paper that it's usable for, I think, tissue. I'm not sure. I have seen it in your papers. Yes. So I was thinking about why, in general, just two theorem are utilized for rather just Gaussian and non-Gaussian. But maybe another option.
I think
Of course. There are always other options.
I think that basically it's an approximation of the sub distribution.
Yeah, right. This was the question: is why using this inverse Langevin congruence theory? It is one approximation. Congruence should be also approximated. You need two approximations, one after another, one on the way to this exact one. Why not directly approximate? This was the idea. It worked more.
This is also because those approximations in probability density functions are analytical, so I can play with them like analytical, or it's not the main motivation of fitting to a Gaussian, for instance.
But Gaussian is, you don't have locus.
Yes,
yeah,
Gaussian.
true. But we use, my question is, we use Gaussian because it's analytical, and maybe we can
It is easy to use, but you are right. So, for example, there is no this chain extensibility limit, right? So it is unphysical. If you look at larger lengths of chains, they are predicted. It predicts non-zero probability. Also, it's not possible, right? So, in this sense, it is not physical. That is why, but it works. Right, still can be used, right? And
to some extent.
yeah, to some extent, right?
Yeah. Okay.
Okay.